Hello AP Chemistry and welcome to weak bases, which basically all the same stuff we talked about for acids, for weak acids, just now flipped from the point of view of bases. Now, so if we have a base plus water, that's going to give us our protonated form, right? Again, conjugate pair, and hydroxide ion, which makes a base, which is why bases are basic, because they leave hydroxide ions in solution. Now, we could write a base dissociation constant expression for this. That would say Hb plus times OH minus gives us our, over our base, right, gives us our Kb value, right? Now, same principle, right? The larger my Kb value, the more basic my species is, right? So something that has a Kb value of 10 to the negative 4 is more basic than something that has a Kb value of 10 to the negative 7th. Yes? All right. So then, that's my Kb expression, and then let's talk about, nope, not that. All right, let's talk about what my weak bases are, right? So my strong bases are my soluble hydroxides, right? My weak bases, we'll note, come in all sorts of weird shapes and forms, right? They don't really follow that same idea as our acids, which is why it's really important that you're familiar with what these weak bases are. So let's talk about some of these, right? So some of these, let's look at the bottom half of this table, right? So here we'll look, these are cations, or these are anions that come from other species, right? So the carbonate ion, right, would normally be part of something else, right? Normally part of an ionic compound, right? This, right, the hypochlorite ion, or the carbonate ion would be part of this, right? This would be part of that. These are all basically the conjugate bases of something else, right? But they have basic behavior. Yeah, does that make sense? Right? So these are all the conjugate bases of other species, and those are going to be one source of our weak bases, right? Conjugate bases of weak acids, right? Now, up here, though, we have a different trend, right? But all of these are similar in that we have a nitrogen with a lone pair, right? So, nitrogen with a lone pair is going to be another of our most common weak bases, right? And in general, these are referred to as amines, right? Whereas like that COOH group, for example, is referred to as a carboxylic acid group, these are referred to as amines, where I have a nitrogen bonded to, right, up to 3 different things, right? Usually hydrogen or carbon groups, right? And we can call them primary, secondary, or tertiary amines, but that's not really what you need to know, right? You just need to know that these are our weak bases. Going back to the definition of a base, right? A Bronsted-Lowry base has to be able to accept a proton. In order to accept a proton, it has to have lone pairs, right? Which is why this part is super important, right? And if we look at what its conjugate acid counterpart looks like, once we add that proton, because protons have a +1 charge, right? We end up with a nitrogen stuck to 4 things, and overall we get a cation, yes? Does that make sense, right? Once we add that proton, the charge goes up by 1, and that nitrogen is now attached to 4 different things, yes? Right? And if we read this formula, this one's easy, right? But here we have a nitrogen, right, stuck to all those things, and this one would be harder. You would have to be able to look at this, right? But here, for example, right, we have the nitrogen stuck to that O, right, and stuck to 3 H's, which means stuck to 4 things, right? Nitrogen is stuck to that carbon, and stuck to 3 H's, which means it's stuck to 4 things, yes? So you need to be able to read these formulas and put 2 and 2 together by yourself. Yes? Really, really important, right? So in general, again, to summarize, right, our weak bases are going to be amines or the conjugate bases from weak acids. Okay? All right, so where do protons attach, just to be clear? So here are some models of ammonia, methylamine, and hydroxylamine. Now, these are referred to again as what kind of models, going back several chapters? Right, ball and stick models, right? Ball and stick models. Now, ball and stick models are great for showing what kind of information about a compound. Right, the orientation of my atoms one to another, meaning it shows our bond angles and our placements in 3 dimensions really well. What does it not show? Ding, 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 it does not show our lone pairs, right? So again, going back to structure, really important. So review 6 through 9 as needed, okay? But we are excluding all of our lone pairs, right? So here, it's up to you to recognize that when we're talking about ammonia, if this is a nitrogen atom, and it's only bonded to 3 things, it's got a lone pair, right? which means that where's the hydrogen going to attach? To the nitrogen, right? That's where my hydrogen's going to attach. Here, right, methylamine, right, if this is a carbon, stuck to 4 things, nitrogen stuck to 1, 2, 3 things, which means there's a lone pair, and my hydrogen will attach here, yes? Okay. Likewise, over here we have a couple of options, right? Here we have an oxygen, here we have a nitrogen, right? And now what do we know? If this is an oxygen stuck to 2 things, what do we know? Right. We know that there are 2 lone pairs here, and since this is a nitrogen stuck to 3 things, there is a lone pair there. Now here it goes back to just which of these is going to be more basic in nature, right? And the answer is the nitrogen. Nitrogens are where our protons are going to attach in an amine style base. All right, so what is the molarity, right, concentration of NH3 that has a pH of this? Okay, so let's talk about what this means. pH of this, and I want to talk about NH3. Here is where, again, recognition. Is NH3 an acid? No. Is NH3 a base? Yes, right? It falls under the nitrogen stuck to 3 things. Is it a weak base or strong base? Right, weak base, right? Which means, does it dissociate completely? No, which means that there's not a direct correlation between hydronium and hydroxide and the concentration of this. We're going to have to work through what value? Right, we need a Kb. Turns out that the Kb for NH3 is 1.8 times 10 to negative 5. So we have that. All right. What seems like a good thing to do? Sure. Let's go ahead and do a reaction. So we have this plus this, equilibrium arrows, right? And that's going to give us what? Protonated form and hydroxide, right? Again, if this is a base, this is what it does in water, yes? So we have our base and its conjugate acid, conjugate base. And we know that this Kb expression is ammonium over, or times this, over NH3. So that's our Kb expression. And we know that we have a pH of 11.17. What can we do with that? Looking at this. Right. If we take 14 minus this, right, what do we get? 2.83 as my POH, yes? All right, so then, let's fill in what we know. So we know that this, irrelevant. Okay. We know that the POH is 2.83, which means that we can turn that into a concentration, right, by doing 10 to the negative 2.83, which is going to give us, I should have put this somewhere else. So anyway, 10 to the negative 2.83 is going to give us 0.00148 molar, right, as our hydroxide ion concentration, which we know is also equal to, right, my ammonium ion concentration. Now, we just have to think about where that goes, right? So this is asking us, what is the molarity of an aqueous solution that has a pH of this, right? So then, this is what we don't know, right? But we do know that this ends up being 0.00148, right? We know that this ends up being 0.00148, starting from what, right? 0, right? And this is plus x, right? And this is actually going to be what then? Right, this is where 0.148, right? Right? Yes? Does that make sense? Right? As in this was something, and this is how much of it dissociated. Yeah? All right, so then we can just set that up, right? So we would have 1.8 times 10 to negative 5th is equal to 0.00148 squared over x minus 0.00148. And we would solve for our x, yes, and work back up to that. Yeah, does that make sense? Because the dissociation is not one-to-one. If this were a strong base, then it would go back to those problems at the beginning of the chapter where if it's a strong base, this dissociates one-to-one. This would also reflect the concentration of that, which is not the case here. Yeah, does that make sense? All right. Thank you for listening. Be good, and I will see you soon. Bye.